Okay, so now we're trying to determine which proton is more acidic. And we talked first about the atom. Larger atoms are better able to bear the charge. More electronegative atoms are better able to bear the charge. The second thing we want to consider, though, is resonance. Resonance has the ability to spread the charge over more than one atom. So let's look at these examples and see which atom is going to be more acidic, either the red one or the blue one. Okay, so if I take off the red one, I will get a compound that looks like this. It'll have a hydrogen here. But if I take off the proton, I'll have a negative charge right here. That negative charge can't go anywhere because it can't go here because we can't make a double bond here because we'd get too many bonds around that carbon, and the same thing here. It's trapped. So all the charge has to be borne by that one carbon. If we take the blue one off, we'll get, here, we'll do a different color. If we take the blue one off, we'll get something that looks like this. Okay, these electrons that are associated with that negative charge can go down here, and that could go there. So we get a resonance figure that looks like this. Okay, so the negative charge is borne by this carbon and also by that carbon. And so that makes it more stable and makes this hydrogen more acidic. You're more likely to lose that one. Let's look at the next example. If we lose the red one, we lose the red hydrogen, we'll get a negative charge here, an extra set of electrons that can't go anywhere. They can't go to the left or to the right because those carbons already have hydrogens on them and they can't take another bond. So all the charge will be borne by that one nitrogen. Let's come over here and look at this one. I was going to do a different color. Oh well. If we take off the blue electron, the blue hydrogen, we'll get negative charge here. But that is adjacent to this ring, and so these negative charges can go here and the charge can go there. So we end up with, you can see this. I'm only drawing part of it. Okay, so the negative charge is there. We didn't do anything to those bonds, so they stay there. This is a double bond. These electrons went to that carbon, so it has to have a negative charge. Okay, now these electrons can go to form a double bond there and push these onto the end. So we'll get okay, good. There, there. That's the rest of the molecule that I didn't draw. Negative charge. Okay. And then finally, one more resonance structure. These electrons here can form a double bond here and push those there. And we'll get so we go back to our original structure. Let's see, we've got a negative charge there. That's our new bond that we just made. We didn't do anything to that one. and the rest of the molecules over here are rest. I didn't draw all of it. Okay. So for this second hydrogen, let's go back to our original figure. If we take off the second hydrogen, the negative is born here. It's born here, here, and here. So we'd expect to find a partial charge, negative charge on all 4 atoms. So that's going to be a lot more stable. And so you're going to lose this hydrogen. Okay, let me get another piece of paper out, and we'll do the last one before we do induction. So the red, which one is going to be more stable? We want to draw them. If we lose the red one, we'll have a negative charge here. We'll have extra electrons sitting there. And they can go visiting. They can visit here and put a charge there. We get a resonance structure that looks like this. The negative charge is down here. We've got a double bond there, and we didn't do anything to that double bond. Then they can push around. You can see why rings are so popular in organic chemistry, because we can get these structures where we kind of chase the electron around, and that's a negative charge there. So the negative, if we take off the red one, this is the red, we get 3 different resonance structures, and the negative charge is born on 3 different carbon atoms. So that's going to be pretty stable. If we take off the blue, we get a negative charge right here. It can't move up here because that would give it too much around that carbon, and it can't go this way because that would be a triple bond. And so it's stuck there, all the negative charge on that one carbon. So this one will be much more acidic. Okay, the other 2 we can do more quickly. There's also induction. Induction is when we have neighboring atoms that withdraw electron density away. So if we look at these 4 compounds, we'll see that the pKa of this one is much lower. That means it's more acidic. Because it's a lower pKa, and that's because the charge is being drawn this way. So what we're doing is we're looking at the conjugate base. So if we take these hydrogens off, we get a negative charge here, right? And that negative charge is stabilized by all this other negative, partial negative charge pulling away. So if you want to identify the most acidic proton in these cases, you'll find the one that's close to these fluorines. So if we put a negative charge here, it's 1, 2, 3 carbons away from the fluorine. If we put a negative charge here, it's only 2. So this one will be the more acidic because it's closer to the fluorine. And here, it's this one. And again, it's because it's closer to the chlorines that are pulling electrical charge away. Now, the 4th and last one is orbitals. If you examine the orbitals, you'll see that the PS2 is the smallest, and it holds the electrons more tightly. So if we look at the pKa of ethane, it's 50. Of ethene, that's with the double with a sp2, it's 44, but acetylene with an sp orbital has a pKa of 25. So if we want to identify, again, the most acidic proton, we first have to find those protons. So we've got 2 protons here and 1 here. And I'm not going to draw in all the sp3 ones. And it will be this one. And again, it's this one. And here it's this one, which is identical to the one over here. Those are the same. Okay. So we want to rank these factors. The most important is the atom, the second is resonance, third is induction, and lastly we look at the orbital. So in the next section we'll be looking at compounds that have more than one factor.